Okay, so we were looking at the uh, metric generated by a point mass and using all the symmetries of the point mass, namely um, spherical symmetry about the point mass and time independence of the solution, we showed that the metric can be brought into a form where you have a GTT component non-trivial, GRR component non-trivial, and the spherical metric was written in a simple form, which was rho squared times d theta squared plus sine squared theta d phi squared. So we just had to determine two functions, which was GTT component, which was written as A of rho, and GRR component, which was written as B of rho. Writing that metric and substituting it into the Richet tensor expression, we got our components to be of this kind. All off-diagonal components of the Richet tensors were 0, and the diagonal components were these four ones: R rho rho, R theta theta, R phi phi, and R T T, of which only three of them are independent. R phi phi is really same as R theta theta up to some sine squared theta factor. What we did after that was to look at certain linear combinations of R rho rho and RTT to show that A of rho and B of rho are inverse of each other, and therefore, if we determine one function, we would determine the second using this relation. Okay, so yeah, then we use the R theta theta equation to determine B of rho by just substituting the fact that the A of rho that appears in R theta theta equation can be kind of traded off by using the fact that A and B are inverse of each other. Then write everything in terms of B of rho. Okay, so once you get that, then we found that B of rho can be written as 1 over 1 plus 1 over C naught of rho, C naught times rho, and C naught was the only constant that we had to determine. Since we know B of rho, A of rho was determined by this relation that A times B equals 1, and we got the metric in this form. Okay, what we had to do was to determine C naught, which of course this set of differential equations would not tell us. Okay, just as a check on this particular equation, we have used the fact that A times R rho rho plus B times RTT is equal to 0. But if you can show that R rho rho is equal to 0 or RTT is equal to 0, it doesn't matter which one you look at, it would establish that the other component of the Richet tensor would vanish. Okay, so checking one of them vanishing is good enough to show that everything is working fine. Okay, because if R theta theta is set to 0, then R phi phi is 0 anyway. Okay, fine. So that is a small exercise that you could do, taking this metric without worrying about what C naught is. You should be able to show that R rho rho would vanish. Okay, but nevertheless, we need to determine C naught, and what we did was we took a non-relativistic limit of the problem, and we decided to use that to determine C naught exactly the way we did for, say, electrostatic problem. Namely, you ask how the TT component of the metric is related to the Newtonian gravitational potential, and once you get the Newtonian gravitational potential, you compare that with the Newtonian potential that we would write down, which is phi is equal to minus g times m upon rho, where m is the point mass of the point particle which is generating this gravitational field. This allows us to identify 1 over 2 C naught is equal to minus gm, and we'll just take that back and put it in the metric, and we would get this metric, which is the Schwarzschild metric that we were looking at. Okay. After that, we said that we of course kind of looked at some basic properties of this metric, namely that rho is equal to 2gm. The metric seemed to have some funny behavior. Rho rho component seems to diverge. GTT component seems to go to 0. but we just said that like this is a coordinate artifact. We can choose the right kind of coordinates in which nothing great happens at rho equals 2gm. The other thing that we noticed was that if rho is less than 2gm, then the d rho squared part would have a negative sign and a dt squared part would have a positive sign. So the time-like coordinate for rho less than 2gm is different from time-like coordinate for rho greater than 2gm. Okay, fine. Then we decided to study motion of a test particle in the background of this particular metric. And since the metric has spherical symmetry and whatever we had learned from the Kepler's law, we knew that if we look at planar motion, then the conservation of angular momentum would tell us that the particle will never get off that plane. Okay, so therefore we chose to study the motion of a test particle in the equatorial plane. And given that you have spherical symmetry, you can convert any plane into an equatorial plane really, so it doesn't really matter as long as as long as the original point mass is in the plane. Okay, you do not look at the plane which is not containing the original point mass. Okay, so once the point mass is on that plane, then every plane can be treated as equatorial plane by using the rotational symmetry. And we'll set theta equals pi by 2 and d theta by d sigma equals 0, just telling you that theta will never change, and which is basically an effect of conservation of angular momentum. So we use that, put it in the geodesic equation, because that is how the test particle would move, where gammas are determined by using the metric that we have. And in this particular case, we don't really need explicit form of A and B to compute these gammas. You can just write down formal A and B and compute these Riemann-Christoffel connections. Okay, so once you get these Riemann-Christoffel connections, as I mentioned last time, that you need to get this even before you kind of do this computation, because this exercise would require computing those Riemann-Christoffel connections anyway. So once you get these, then you realize that these are the only non-vanishing ones, other ones would just vanish. Okay, so what we did was we set up the equation and we looked at the rho equation, which contains all kinds of terms, but many of those terms contain, like one of the terms contains d sigma, sorry, d theta by d sigma, which would be 0 because that is our initial condition. Okay, and one can use these to kind of simplify this equation, write it in a particular form. The phi and t equations are even simpler, and one could kind of show that these equations can be simplified by, which we'll do in a moment, by kind of multiplying d sigma by dt to this equation and d sigma by d phi to this equation. Okay, and so we did that. We found that by multiplying d sigma by d phi to this equation, you can show that this is a logarithmic derivative equation, and that tells you that rho squared d phi by d sigma is some constant. And similarly, doing the same thing with t equation, you find that a of rho times dt by d sigma is another constant. And what we did was we set this constant L to 1 by just rescaling the affine parameter. Okay, and that allowed us to write down dt by d sigma to be 1 by a of rho. Okay, so using these facts that dt by d sigma and d phi by d sigma are known, we can just go back, plug it into the rho geodesic equation. You have dt by d sigma, d phi by d sigma already. So take that and just simplify the equation. And what happens is that if you substitute that, you can write this equation as a total derivative of b rho times d rho by d sigma whole squared minus 1 over a rho plus k squared upon rho squared. And therefore, the quantity in the parenthesis must be constant. Okay. Uh, Fine. So that is one thing that we had noted last time. And um, if you use the d phi by d sigma and dt by d sigma equation, you can get rid of the affine parameter and write down a equation for dt by d phi, sorry, d phi by dt, and similarly you can write down an equation for d rho by dt. Okay, so those are the two equations also we had determined last time. Other thing that we noticed was that if we work on a equatorial plane, then the line element itself takes a form which is uh, minus a of rho times dt by d sigma squared plus b of rho times d rho by d sigma squared plus rho squared times d phi by d sigma squared, which is precisely the same number n that we had looked at here, say this quantity. Okay, so so of course that requires us to substitute what is dt by d sigma and what is d phi by d sigma. But once you do that, you find that the expression turns out to be this, which is exactly this constant. In other words, this constant n tells you uh, about what is the nature of the test particles. Because if deta by d sigma whole squared is some number here, if this number is 0, then it is actually a line element corresponding to a massless particle. If that number is negative, then it's a line element corresponding to a massive particle. Okay, so therefore this n that we have obtained by solving the rho geodesic equation actually carries the information about what kind of test particle one is looking at. Okay, so we can use this fact to eliminate this function and write it in terms of n, and uh, so what we could do is that we can take these two equations and write down rho as a function of phi and eliminate t completely. Now notice that the metric was independent of t anyway, so by eliminating this, you can actually figure out how the azimuthal angle changes as the particle, the test particle's radial position changes. Okay, and that is what gives us an equation which is d rho by d phi is equal to 1 over k times rho squared times square root of this quantity that we have kind of looked at earlier, which is b rho times d rho by d sigma whole squared, which is n minus k squared by rho squared plus 1 over a. Okay, which is this quantity. Okay, so you can of course write it in many different ways. If you want to ask, well, how does the azimuthal angle changes, you can just replace it in this particular form, and that is the equation that we would like to look at, because we would have thought that the particle would travel in straight line if there is no non-trivial metric. But if the particle is kind of changing its azimuthal angle, then clearly the particles seem to be kind of following a curved path. We want to ask what happens if we try to consider the particle to be massless, namely light light quanta. Okay. Now, of course, if you are looking at a question of bending of light, that means we'll have to set n is equal to 0, because that is what this statement tells us. Okay, that if n is equal to 0, we are looking at massless particles. So bending of light would require us to set n is equal to 0 and try to study this problem. Okay.
Sir,
Yes.
sir, to get from this equation to, let's say, Newtonian gravity,
Yeah.
so we have to set n to 0 for photons and a to and b to be 1. What else, sir? Uh,
Uh, which equation? This
I am
equation.
not sure. Yeah.
Yeah. So see, the thing is that like in the Newtonian case, you don't kind of in the Newtonian problem, the speed of light is infinite, right? I mean, okay. So you have to also have to take non-relativistic limit of this thing. Okay.
And sir, how does it work?
Yeah. So I mean, usually what one does is that like once goes back to the non-relativistic thing and not take a limit of this problem. But if you want to take the limit in this
Oh,
particular, yeah,
okay. Okay.
yeah. But like if you want to take the limit, you basically have to set a and b equals one, and compute this quantity by setting n also equals to zero, basically. Okay, you do that way and compute. Okay, in fact, what
So the only
Laplace?
f-
Uh, yeah,
so the only factors of C are in A and B, right?
yes, yeah,
So that anyway will set that equal to one.
yes,
So
exactly, yeah. Yeah. But like n is equal to zero is not really a non-relativistic input. It's actually a relativistic input, right?
yes,
That
yes.
d tau squared is equal to zero is not something which Newtonian mechanics would have told. So you need to do that to get there. So in fact, this kind of computation was done by Laplace and had computed the bending of light due to purely Newtonian effect, which is of course uh, half of what is the general relativistic effect. And that's why um, it's not like doing this exercise experiment to check whether the light is bending is is not good enough check of general relativity, but to get the bending angle to be twice as much as what a non-relativistic physics would have given was a crucial test. So in that sense the I think Eddington's experiment was very important in 1919 to get that factor of 2 right, really.
So he did all this from Newton, starting from Newtonian,
No, no, no.
not from this.
No, the calculation was done Laplace. Laplace did it purely from Newtonian long before GR.
Yeah, because Laplace was
Yeah,
at the time of Newton. So
yeah, yeah. I mean,
yeah,
little after him. Yeah. So
yeah.
that computation was done purely Newtonian mechanics computation. But Einstein also did this computation after general relativity was results were put out, and initially he also made a factor of 2 error, and he got the same bending as Newtonian. This thing later on learned that he missed a factor of 2, and that factor is crucial because that is the one which distinguishes non-relativistic Newtonian gravity from general relativistic gravity, and the experiment in fact confirms the general relativistic effect. Uh, that means that bending is twice as much as what you would have expected. This thing. So yeah,
Okay, sir.
that is the thing. Okay, so what we'll do is that we are going to look at the passage of light, and you want to ask how the trajectory of the light would bend because of the curvature of space-time generated by a massive object. Okay, so we will assume that the distance of closest approach for the light is uh, some value of rho, which we call rho naught. Okay, so uh, so the value of rho for the light uh, particle or wave, whatever you want to call it, is values of rho which are greater than rho naught, greater than or equal to rho naught, but not smaller than that. Okay, so at rho is equal to rho naught, we would kind of course, extremize the uh, equation. That means we will say that d rho by d phi would vanish at that point. Okay, so that if you put it back here, d rho by d phi vanishing at that point, it tells you that 1 over a of rho should be equal to k squared upon rho naught squared at k squared upon rho squared at rho equals rho naught. Okay, so that is because you want to set this equal to 0. These are all non-trivial quantities. They cannot vanish. Okay, so therefore the numerator has to vanish, but n is equal to 0. So you set this two quantities equal. Okay, so that tells us what is k. Okay, so k is rho naught square upon a of rho naught. Okay, so what we could do is we can put this back into our expression. So our expression for d phi was this. We put k is equal to rho naught square upon a of rho naught, and just massage the equation a bit. Uh, actually, uh, and that is just pull out a of rho naught outside, and you get an expression which looks like this. Okay. Fine. So this is of course an exaggerated image. It doesn't bend as much as this much, but like my drawing quality is also kind of as bad anyway. So here's the thing that the initially the particle or the light was moving this way, and the impact parameter is of course the closest approach of this straight line from the scatterer, namely the point mass. That is what we call B. Okay. The distance of closest approach is of course less than B, simply because it's an attractive force and it will bring this closer to the particle, and it will kind of bend over and kind of go in some direction. Bending of light is of course the angle between this asymptotic straight line and this asymptotic straight line. It doesn't look like a straight line, but let's take it to be so. Okay. And the angle generated by these two. Okay. This angle is of course pathetically small compared to the way I have drawn it. This looks like almost more than 60 degree, but the actual angle is really in uh, less than a degree, in fact, uh, tenths of degrees and so on. Okay, fine. So what we want to ask is, what is this asymptotic value of d phi? Okay, that the initial light is this way and outgoing light after scattering is this way. Okay, good. So what we will do is not do this computation, but what we'll do is that we'll do this computation of incoming light. Okay, and uh, integrate its path from infinite minus infinity to rho naught. Okay, that's what we will do. Okay, so of course to determine what is delta phi, we have to do the same computation from rho naught to infinity. Okay, but if you think about the problem, then you will realize that whatever happens from rho equals minus infinity, well, there's nothing called rho equals minus infinity. Rho is positive always. So rho equals infinity to rho naught, and from rho naught to rho equals infinity again. This problem is completely symmetric. So whatever is a bending that you get here, you should double it, so that delta phi is actually twice as much as the angle that you obtained when you did the computation from infinity to rho naught. Okay, fine. So what we are going to do is basically do this computation and use the fact that A of rho times B of rho is equal to 1 and simplify our life a bit. Okay, so this is a little bit of massaging of this expression to write it in this particular form. It looks a bit nice and symmetric in the denominator, and the numerator piece just gets eliminated. So life is kind of easier. Okay, so now what we are doing is just substituting these functions. We just write A of rho naught is equal to 1 minus 2gm by rho naught. These are all numbers now because rho naught is a fixed value. A of rho is of course 1 minus 2gm by rho, and these are all functions. Okay, and we have to do this integral. Okay, fine. So as I said, that the bending is really tiny for for uh, say objects like sun, some stars of that kind. Unless you are really looking at supermassive black hole or some such thing, you don't really see much of a uh, significant bending. So therefore, what we will do is we will do approximation while solving this integral, uh, because the bending is effect is small. Okay, fine. So here's the thing: we write down d rho upon rho square. This set is set to 1, and we expand this expression by saying that rho is always greater than rho naught. Okay, so therefore 1 minus 2 gm upon rho is larger than 1 minus 2 gm upon rho naught. Okay, because uh, rho is larger than rho naught. Okay, so what we'll do is we'll pull out this factor, which is a bigger number. Okay, and take the remain other piece and expand. Okay, so we'll expand the square root. Just a second. Okay, so coming back to this thing, um, so we what we'll do is we'll pull out 1 minus 2 gm from the square root and uh, and expand that quantity in the numerator. Okay, so and we expand that simply because we are taking value of rho which are larger than 2 gm. In fact, value of rho naught is also larger than 2 gm. We are not trying to get into the region where rho is less than rho naught anyway. Okay, uh, so so 1 minus 2 gm by rho, when you pull it out of the square root and expand, you get a term which is 1 plus gm upon rho. The factor of 2 goes away because of the square root term sitting around. Okay, because when you pull this out, you get 1 minus 2 gm by rho whole to the half, and its binomial expansion would kind of eliminate the factor of 2. And the other expression that you have, you can just expand it downstairs in this expression, and you get terms of this kind. Okay, good. So again here, what we are going to do is 1 minus rho naught square upon rho square. Uh, this quantity we can pull out. This is of course a quantity which is positive because rho naught is less than rho for almost all values. Okay, so when you pull it out, you can write down this expression as 1 minus 2 gm upon gm times 1 over rho naught minus 1 over rho times this entire quantity. Okay. Okay. So they are just sequence of simplifications. So we have already expanded the one of the terms in the numerator, and now we're going to expand another term in the numerator, namely this piece, and we're going to put it upstairs. Okay. Fine. So uh, so when you expand this piece, you again get, because of the power of half, you get a factor of 2 missing again here, and you can write down this expression. Okay. There's a little bit of massaging needs to be done. If you look at it a little carefully, you'll see what's happening. Uh, when you have a factor which is 1 over rho naught minus 1 over rho, which can be written as rho minus rho naught upon rho naught. One of the rows would kind of cancel out with this. Rho minus rho naught will cancel with one of the factors here, and you are left with rho plus rho naught. Okay, and uh, the terms that are left over is rho upon rho naught, which is here. So rho upon rho naught, and this will give you a rho plus rho naught factor. Okay, but the term that you get when you write down this with a common denominator is rho minus rho naught piece, which you need to cancel from here, and you get an expression like this. Okay, the sign plus here is because this to the minus half is being expanded in the numerator. Okay, so that switches the sign out there. Okay, fine. So a little further simplification of this would land you up with an expression like this. Notice we are ignoring terms which are proportional to g m whole squared, which are the terms which are sitting in the ellipsis. Okay, so we are really looking at effects which are uh, linearly dependent on the mass of the particle. Okay, fine. Now, what we want to do is to do this integration either from infinity to rho naught or from rho naught to infinity. It doesn't matter which way you do it. Okay, so we are going to do it from rho naught to infinity. Okay, so here is the integral. So on this side, you know that this would correspond to the value of phi at infinity minus value of phi at rho naught. Okay, uh, the right hand side is the integral over rho, and that should be a quantity integrated from rho naught to infinity. Okay, good. So the best way to do this integral is to change variables, kind of get your integration limits also changed in the process, and that is done by substituting rho is equal to rho naught times sec theta. Okay, and if you do that, then you get d rho is equal to rho naught sec theta tan theta d theta, and rho square minus rho naught square becomes rho naught square tan square theta. Okay, so that simplifies this expression quite a lot, simply because When you do this, d rho upon rho becomes a simpler expression. Similarly, a square root of rho squared minus rho naught squared becomes a simpler expression. Okay, and when rho is equal to rho naught, you get theta is equal to 0 because uh, uh, at that point, uh, when rho is equal to rho naught, this quantity has to vanish. Okay, uh, fine. When rho goes to infinity, of course, at that time rho squared minus rho naught square is very large, is infinite, and in that case theta goes to pi. So therefore rho naught would be replaced by theta equals 0, and infinity would be replaced by theta equals pi by 2. Okay, sorry, maybe I said pi, but yeah, it should be pi by 2 because tan of pi by 2 is infinity. Okay, so therefore this integral is replaced by a new dummy variable integral theta. Okay, and it takes the form of this kind. Okay, and you can see a lot of things get cancelled. Rho naught gets cancelled, sin theta tan theta also gets cancelled, and you get a pretty simple integral. Okay, fine. Now this integral also can be further massaged by kind of writing down 1 plus cos theta is equal to 2 cos squared theta by 2, and you can write that in terms of sec squared theta by 2, and remember that the derivative of tan is sec squared, so therefore this would be related to a inside the integral this would give you a tan angle. Okay, so um, so that is a kind of effect that you will see when you do this integral. You one would give you just pi by 2. This quantity you can compute, you get g m upon rho naught. Okay, because this will give you a sine angle, and sine angle at the lower end doesn't contribute anything, at upper end would give you just 1. Okay, this quantity can be written in this particular form by just doing the integral of this expression, and uh, and when you substitute these quantities, phi naught, phi infinity minus phi of rho naught gives you this expression. Okay, pi by 2 times gm upon rho naught. Okay. Now, of course, as I said, that the total change in angle should be twice as much of that, because you are taking this really a formal rho equals minus infinity statement. That light really starts at very large rho, which I want to call that minus infinity, although rho is a radial variable, and goes to rho equals plus infinity. So what we want to do is to kind of double the angle. Okay, so this will become pi, and this will become 4 gm upon rho naught. Okay, now pi is nothing very special. Pi would just mean that your trajectory just went like that, right? That is uh, the angle pi. Okay, so the deviation from that is what is delta phi. Okay, so therefore uh, delta phi is really going to be 4 gm upon rho naught. Okay, so this is the angle by which the light would deviate from its original trajectory when it is passing by a very massive body. Okay,
So,
yes.
so will there be any redshift or blue shift effect along with this?
Uh, yeah, of course there will be effect, but you see that that effect you wouldn't observe because a particle, I mean, the light is coming from infinity with some frequency, okay, and the light is detected again at infinity, right? So the frequency that you would measure would be essentially the same frequency that it originated with, okay. The redshift blue shift effect you would measure only if you are in the vicinity of a massive object, okay.
Okay.
Okay, so we will study gravitational redshift later, but redshift effect is something if that you would notice if light is emitted at, I mean, in this particular example, say light is emitted at some rho value and is detected at some other rho value. Okay, what we are actually doing is we are in both cases the rho value is very large. Okay, so there is no redshift effect that you will see. Okay, okay, so the exercise basically or the experiment basically that we want us to conduct is to kind of study bending of light, say when there is total solar eclipse, and you substitute m to be the mass of the sun, and you kind of estimate what would be the closest approach for the light, uh, uh, which is bending due to the gravitational field of sun. Okay, the reason why we are doing gravitational field of sun, or they did gravitational field of sun because that was the uh, nearest massive body which could affect bending of light. Okay, now of course we have much better techniques of doing this. We can see bending of light due to galaxies, due to supermassive objects and things like that. There's something called uh, some interesting effect called gravitational lensing, which is essentially the effect due to bending of light. Okay, and it's one of the very interesting topics within astrophysics. And when they study various objects in the sky, you need to definitely weed out what are the objects that you see are just images of some other object that you are seeing. Okay, so now of course gravitational lensing for very distant objects produces a very finely separated images, but nevertheless you need to kind of weed them out because they are all same objects. Okay, the other thing that we could do while studying the geodesic equation is to study bound orbit. Okay, so this is what we are studying is kind of in a reverse order compared to what we would have done, say, in classical mechanics or in quantum mechanics, in the sense that like in both these subjects, we usually study bound state problem first, scattering problem later. But what we have done just now is we studied the scattering problem first, which is what we call bending of light, and we are studying the bound state problem later. Okay, but it doesn't matter. They are in some sense kind of independent studies, and although uses the same set of equations. Okay, now if you are looking for a bound orbit, but maybe before that, any questions about this bending of light? Okay, maybe not. Maybe you can look at the bound orbits again. So, so when you are looking at bound orbits, so unlike what we did in the bending of light case, where we said that the particle started at large value of rho, came close to the object, the point of distance of closest approach was rho is equal to rho naught, and then it went away again for large values of rho. Now that's not what would happen in the case of bound orbits. Bound orbits would have rho values which have a lower limit and upper limit. Okay, so therefore we want to ask a question as to how does the angle phi, the azimuthal angle phi, change as we uh, study the motion of a bound object. Okay, uh, where the radial variable is bounded between two values, which we will call rho minus and rho plus. Okay, so so roughly the picture would look something like this. Okay, don't worry about the quality of the picture, but the orbit is like this. It will go large value of rho, drop down, come to the smallest value of rho, goes up again, and so on. Okay, but it will continue oscillating between these two values only. Okay, fine. So so we basically have to kind of use the fact that it doesn't matter what is the value of phi, the rho values are always bounded. Okay, good. So in addition to kind of this thing, what we will see that d phi by dt, which is given by Ka upon rho square, this quantity would always be positive for all positive k. Okay, so now a bounded orbit means you are looking at something like this, then there exists some values of phi at which d rho by d phi would vanish. Okay, and we know what are the values of rho for which these things will happen, and that is when rho is equal to rho plus and rho is equal to rho minus, which are the extrema of this curve. Okay, so we are going to set d rho by d phi equals 0 exactly at this rho is equal to rho plus and rho minus. All we need to do is to kind of go back to this equation, set this quantity to 0 for rho is equal to rho plus or rho minus. Okay, so nothing special happens with these functions, so we look at this. Okay, and we find n minus k squared upon rho plus or minus squared plus 1 over a of rho plus or minus is equal to 0. Okay, now in this particular case, we are going to look at a very specific kind of particle. If you are looking at bound orbits, you are looking at some kind of planetary motion, and the object is massive and stuff like that. So we are going to take n to be some fixed value. Okay, we will not worry about what that value is. As long as n is negative, we are fine. Okay, so what we will do is that we will take this equation, and if you subtract this equation for rho plus and rho minus, the n would get eliminated. Okay, so we get this expression, and using this expression, we can determine what is k. Fine. So this is the value of k. This is a kind of trivial thing. You just take common denominator and invert this entire stuff on the right hand and write it on the right hand side. Okay. Fine. So once you have determined k squared, we can just put it back into this equation. Okay, here, and we can, or even here, and we can kind of get an expression which looks like this. Okay, so so all we are doing is we are working at the extremal values of rho, and we have just replaced k squared by this entire expression, and we of course have rho plus squared or rho minus squared. We have like equations of that kind. Okay, good. So you can kind of massage this equation further to determine what is n. Okay, in terms of a rho plus, a rho minus, as well as rho plus and rho minus. This is the expression. Okay, so a little bit of kind of massaging of this. You multiply by rho minus squared times rho plus squared everywhere. Rho plus squared cancels out here, so you have a rho minus squared times 1 over a rho plus minus 1 over a rho minus, and this would have a term which is rho minus squared minus rho plus squared, which is multiplying the entire equation. Okay. Now you can see that even here some of the terms would get cancelled. Rho minus squared upon 1 over a rho plus cancels here, and it's replaced by this quantity. Okay, it's a nice symmetric function. Rho plus squared upon a of rho plus minus rho minus squared upon a of rho minus. Okay, good. So we will take this n, this k, and substitute it up into this equation. Okay, fine. So when we do that, we get some messy expression out here. I should probably try explaining this thing in a few steps. So if you go back here, you have a square root of b of rho sitting around here. You want to actually write this expression for d phi. Okay, so that's why you are kind of inverting this. Your square root of b of rho is in the numerator here, simply because this, here, simply because you are writing d rho by d phi. If you write down d phi by d rho, this fellow is in the numerator, this fellow is in the denominator. Okay, so b of rho sits in the numerator. This expression with n k squared substituted takes the form like this. Okay, as you can see, there is a minus half power. This term is equal to n, and this term is equal to k. This factor times this factor. Remember, you have a k squared by rho squared. Okay, so this is a k squared, and you have a k squared by rho squared. So you see there's a 1 over rho squared outside, and this entire expression is just k squared. Okay. Fine. So far we have not said what A and B were, but now we can substitute A and B in this expression. And and once you substitute that, we are looking for solutions where both rho plus and rho minus are greater than 2gm. Okay, so we are always going to be in the case where nothing special happens to the Schwarzschild metric that we are studying. Okay, okay, so so let's do that. Since rho is much larger than 2gm. Okay, so maybe I should kind of say why one is kind of in is kind of doing this kind of approximation, just to give some idea as to what are the scales of these things. The 2gm radius, which is what we would call Schwarzschild radius of the object. Suppose you want to try to ask this question about, say, the sun. That means m is the solar mass. Okay, then the factor 2gm is roughly of the order of few centimeters. Okay, that would be the Schwarzschild radius of the sun. Okay. Uh, on the other hand, the distances that we are talking about are the distances of the planets. Like, even if you look at, say, the nearest planet, say Mercury, okay, the the radius, if you imagine Mercury's uh, orbit to be, say, completely circular, okay, which it is not, but nevertheless, if you assume that to be circular, the rho value, the radial value of that orbit is much, much larger than the Schwarzschild radius. This is Schwarzschild radius for the sun is a few centimeters, some something like 40 centimeters, something like that. On the other hand, it's in like, millions of kilometers is uh, the radius of the orbit. So therefore, it makes complete sense to say that rho is much, much larger than 2gm. Okay. Uh, this thing may not be true if you are looking at objects which are what are called black holes, and in that case, of course, one needs to uh, ask a little different question. Okay, but right now we are really looking at massive object which is more like a star. Okay, and also another thing that you would kind of immediately understand is that if the Schwarzschild radius of sun is of the order of few centimeters, okay, yeah, a few tens of centimeters, same, then the sun, of course, is much, much bigger than that itself already. Okay, so therefore, mm, its Schwarzschild radius is way inside its own uh, uh, body. Okay, and if you try to approach that Schwarzschild radius, then clearly the Schwarzschild radius would continue receding, in the sense that, like, the amount of mass which is outside the Schwarzschild radius is much larger than the amount of mass inside the Schwarzschild radius. And therefore, if you go a few centimeters worth of distance, say, inside the stellar body, like star, like sun, the actual mass inside that is much smaller, and therefore the Schwarzschild radius generated by that mass is even smaller, and therefore you actually never cross the Schwarzschild radius if you're looking at stars of the type of our sun. Okay. Uh, so you really see this kind of non-trivial effect if the object is smaller in size than its own Schwarzschild radius. Okay, and most of the stars are not of that kind. Okay, black holes, of course, are. Okay, so because rho is much, much larger, it makes a lot of sense to kind of expand square root of b of rho and write down a leading term as 1 plus gm by rho. Okay, whereas b of rho is actually this quantity. Okay, similarly, a of rho plus minus inverse.
Sir,
Is also yeah.
sir, while deriving the Schwarzschild metric, we assume the a Dirac delta source.
Yes.
So this even doesn't make sense. Uh, to have to for sun to have a finite size.
No, that is right. That is right. But when you solve, say, Kepler problem also, you assume that the sun to be point mass, right?
That is not true, right? Uh, like we don't consider it to be a point source. We just consider that our equation is valid in a source-free region, and it's coming
That's
from
right.
a spherically symmetric object.
Yeah, that is what we did right now also. We just solved it
Yes,
in a
yes.
source-free region.
Yeah,
But
I mean
but
it can be a extended object also, which is spherically symmetric.
certainly, but what aspect of that extended object have we used in doing the calculation? Nothing really, right?
Yeah,
Only spherical symmetry,
yeah. So I'm
right?
saying that what he started with, like the Dirac delta source, that is not a necessity.
That's not necessary, but the if you solve Kepler like problem, okay, or even this problem, okay, the finiteness of the size of the object hasn't actually been folded in any of these calculations. Okay, only thing that we have used is spherical symmetry of the object. Okay, and solved it in source free region. Now we solved it in source free region for and allowed it for all values of rho. Okay, but you could say that okay, it's not true. It is valid only for certain values of rho greater than say rho hat. Okay, what I'm trying to say is that rho hat is much smaller than 2 gm. Okay, if that is the case, then you would call that object to be a black hole. If that rho hat is larger than 2 gm, then you would call it a star. In that case, many other phenomena that you need to take into account and not really treat the problem in this fashion. Okay, is that fine?
Yes, sir. My only point was that rho is even bigger than the size of the planet. So rho
Size of
is
the star,
already,
you mean?
yeah. Sorry,
Yeah,
star. Yeah,
certainly.
yeah.
Rho is bigger than the size of the star. What I was just trying to give you a kind of estimate as to what would 2 gm be, say if you are looking at sun. Okay, and it would be a very tiny object. So rho is really huge compared to the value of 2 gm, and therefore this expression that rho is much greater than 2 gm is quite sensible for most of the luminous stars. Okay, uh, in case of black hole, this may not be true. You may actually be able to access the regions where rho is of the order of gm. You may even be able to access, a region where rho is less than 2 gm. Not classically, of course, but if you want to study quantum gravity, you may even want to ask a question: what happens when rho is less than 2 gm, and whether you can kind of make sense of physics across rho equals 2 gm. Okay, Mm, so which is a different point compared to what we are trying to do right now. We are just trying to look at bound state solution uh, for a metric of this kind. Okay. So I was not really trying to make very rigorous statement about we have actually used the point mass and stuff like that. All I'm trying to give you an idea is that suppose you look at a realistic star-like object, what would be the Schwarzschild radius of that luminous star? Okay, as against say black hole. Okay.
Okay, sir.
Okay. So coming back to this, so we can simplify B of rho. Okay. Then there is this term sitting inside the square bracket. So we can kind of try to massage that expression in the square bracket. It's quite a uh, messy stuff. But once you do an expansion of this A of rho in this particular form, then you can kind of substitute. Remember, A of rho plus rho minus both are sitting in the denominator. So this expansion can be just put in and you can kind of simplify the expression. Okay. So so this expression is actually messy. It runs over 2 pages really. I mean across the page rather. Okay. So you can kind of substitute this behavior of A of rho plus and A of rho minus expanded in this form and you get a variety of terms. You can check what they are. You have a rho plus square upon a of rho plus, which is expanded like that. Rho minus square upon a of rho minus, which is exactly same with rho plus replaced by rho minus. And then there are other two terms like this, which are again rho plus and rho minus, with this function multiplying it, 1 over rho squared times rho plus minus rho minus whole squared upon rho minus square minus rho plus squared times a of rho plus minus a of rho minus, which is rather inverse of those, which are these expressions. And then a of rho also can be expanded in this fashion, simply because a of rho with rho larger than rho plus, if a can be expanded, rho larger than rho minus, if a can be expanded for rho minus this way, it can be expanded for rho. So you write down expressions like that. Okay. Fine. Now, now if you look at this expression, you have all kinds of terms, but all these terms have the feature that they involve negative powers of rho. Okay, there is nothing with positive powers of rho. These are the pieces which are independent of rho, and these are the pieces which contain different powers of rho. There are terms involving 1 over rho terms, and then there are terms involving 1 over rho squared pieces. Okay, so the highest power is 1 over rho square. So therefore, you have 1 over rho square, 1 over rho, and constant piece, which is this and this. So in principle, this is a quadratic equation in 1 over rho. So you can write the square bracket as some constant times 1 over rho minus 1 over rho plus times 1 over rho minus 1 over rho minus. Okay, and this decomposition is clear from the trajectory itself, right? That the trajectory kind of has the derivative vanishing at rho equals rho plus and rho minus would guarantee that this square bracket has to have zeros sitting at these points. Okay. So of course one has to determine what C is. Now the entire expression is quite messy, but we should be able to figure this out by kind of looking at the term proportional to say 1 over rho squared. Okay. So suppose you look at a term which is proportional to 1 over rho squared, its coefficient is C. Here we have to look at the terms which are proportional to 1 over rho squared and ask what is the coefficient of that term. Okay. Now that involves a lot of terms. This entire line up here and this term. Okay, so we put all of them together. You have 1 over rho squared times. I'm not able to fit this in a single screen, but anyway, so there is a 1 over rho squared times this piece times this entire term. Okay, so is a rho plus rho minus whole squared upon rho minus squared minus rho plus squared times a rho plus minus a rho minus. Okay, so check that out. Is rho plus rho minus whole squared upon rho minus squared plus minus rho plus squared times a of rho plus minus a of rho minus, and this is the last piece, which is 4g squared m squared upon rho squared. Okay, fine. So you can kind of massage these expressions. You find that constant pieces cancel, 1 over rho pieces kind of can be combined into this form, and rho plus rho minus pieces, 1 over rho plus rho minus squared pieces can be combined in this form. Okay, there are different orders in GM. One is linear, one is quadratic. Okay, good. So you find that this term has a coefficient which exactly cancels the fellow sitting around here. So you get minus 1 over rho squared times 4g squared m squared and a plus 4g squared m squared upon rho squared. So it just cancels out and life becomes much simpler. One of the rho plus rho minus terms cancel out here. This has the factorization rho minus plus rho plus rho minus minus rho plus cancels and rho minus plus rho plus survives. So this is the eventual expression. Term quadratic in G and M cancel out, term linear in G and M simplify. Okay, and you can of course, we know that this can be written as partial fractions in this particular form. Okay, so that is it. The term proportional to 1 over rho square, which was C, okay, can be read off from here. It is minus 2gm upon 1 over rho plus 1 over rho minus inverse. Okay, fine. So what we could do is we can take this complicated expression in this square bracket and replace that by C times 1 over rho plus 1 over rho plus, sorry, 1 over rho minus 1 over rho plus times 1 over rho minus 1 over rho minus. Okay, this is just a square bracket, but we'll have to take a square root of that. Okay, so we'll just plug this up here to the minus half. Okay, that is the power. Okay, and now we can substitute b of rho, which we had already said is 1 plus gm upon rho. Okay, plug that in and kind of compute. Okay, now to do that, you also know k, which was obtained. Sorry, I have to roll back quite a lot. K was obtained out here, so we can, and we know what is a of rho and a of rho plus and rho minus, which were written out here. So we need to plug this other messy equation, but it can be simplified. Okay, so you have this term, and this is 1 over a plus minus 1 over a minus. We know how to simplify this expression, collect terms which are linear in GM, collect terms which are quadratic in GM. Okay, and this expression can be written kind of in this particular form, and you can show that 1 over rho plus minus 1 over rho minus term actually cancels out because there's a piece sitting around here, okay, which cancels everywhere, and 2gm factors out, and you get an expression which is 1 plus 2gm times 1 over rho plus 1 over rho minus. Okay, good. So many of these quantities are just constants, but they are useful quantities. They simplify some of these expressions. Okay, so now remember, this is k squared. We really want k in our expression, as you can see. So we have to take a square root of that. So you get a root 2gm, this to the minus half, and this to the half, which of course we will expand again and write that as 1 plus gm upon 1 over rho plus 1 over rho minus. The factor of 2 goes away in the binomial expansion. Then you have a d rho upon rho square, and then you have a 1 plus gm by rho. Okay, and then this entire piece, okay, which is written out here. Okay, so look at this one. You have a 2gm to the minus half and 1 over rho plus 1 over rho minus to the plus half. Okay, so that is how this will appear. Okay, so again, a lot of cancellations. You can see these terms cancel, this term would cancel, and you are left with only terms of this kind. Okay, fine. So there is a constant piece sitting around, which we will not worry about. We will just write at the end, right here. Then there is a d rho squared upon rho squared into 1 plus gm by rho, which is this piece, and 1 over rho minus 1 over rho plus times 1 over rho minus 1 over rho whole to the minus half is a piece sitting around here. Okay. Now this integral is doable if you kind of as it is. If you forget about this constant, that's not important. But if you just plug this into, say, some symbolic manipulation packages like Maple or Mathematica or something, it will just give you the answer right away. Okay, it's not very difficult integral, but it also can be done by change of variables. So what we can do is we can write down 1 over rho is equal to z, and if you do that, then d rho upon rho squared is just minus dz. Okay, so you can kind of make this expression look simpler by doing something like this. Okay, this quantity, which is 1 plus gm by rho, would become 1 plus gm times z. Okay, the rest all are just constants. We don't even need to worry about them. Okay, Now the square bracket that we have can be kind of manipulated and written in a particular form. You can write that as 1/4 times 1 over rho plus minus 1 over rho minus squared minus z minus half of 1 over rho plus 1 over rho minus whole squared. Okay. If you expand this term, then it involves several pieces which cancel out and eventually give you an expression like that. Okay. But advantage of doing this is basically something which tells you that what are the range of z and what is the center around which the z is defined and what is the shift of value of z. Okay. So we could use this fact, and given that it is written as a quadratic equation, we write down z minus half 1 over rho plus 1 over rho minus, okay, is equal to, so notice this quantity that you can write this as some sine function. One of the reasons why we want to use trigonometric functions is because our orbit is periodic. Okay, so therefore it should be writable in terms of a trigonometric function. So this is like, if it's like 1 minus x squared kind of thing, which would give you an idea that you would want to write this quantity as sine function. Okay, but this is not exactly 1, this is some other variable, but it doesn't matter. That is just the radius of the circle. So you write down z minus half 1 over rho plus rho 1 over rho minus is equal to this radial factor times sine a. Okay, so you trade off z by a. So dz would be written by this quantity times cos a dA. Okay. Okay, so what is the advantage of doing this? If you use this, then you replace z minus half of 1 over rho plus 1 over rho minus by half of 1 over rho minus 1 over rho plus times sine squared, sine a, of course, whole squared. So you can pull this factor of 1/4 into bracket 1 over rho plus 1 over rho minus whole squared and write down that as 1 minus sine squared a, which is cos squared a. Okay, so the entire square bracket is just this number times cos squared a. Okay, dz is of course cos a times dA. Okay, but this cos is in the numerator, whereas this cos will be in the denominator because of minus half power. Okay, so life becomes simpler because, of course, there is one more sine a sitting around because of this gmz, but this entire piece, a square bracket with minus half power times dz, the cos angle would just cancel out. Okay, so what you get is various numbers which we of course have to worry about. So d phi is equal to minus half 1 over rho minus 1 over rho plus cos a dA, which is coming from dz, and then the square bracket gives you half 1 over rho minus 1 over rho plus whole inverse times 1 over cos a. So you can clearly see a cos a going away. Okay. Z, of course, is not a very simple variable because it is this function plus half of 1 over rho plus 1 over rho minus. Okay, so when you substitute that in gmz, you get two terms, but that's not very complicated because one of the terms is just a constant, the other term is sine a, and therefore it should be possible to integrate. Okay. Limits of integration are not very difficult to determine. You know that the maximum value that rho would take is rho plus, the minimum value that it can take is rho minus. Okay, so based on that, you can kind of determine what would be the values of z. Okay, use those values of z to determine what could be the values of a. Okay, so here is a statement that when is rho is equal to rho minus, which is the smallest value that rho can take, z would be 1 over rho minus because that is the inversely related expression. Okay, but when z is equal to rho minus, then you can put it back into this expression and you check what happens when z is equal to rho minus, that would kind of flip the sign of rho minus here, because 1 over rho minus minus 1 over 2 rho minus will give you 1 over, I mean, it will give you minus half of rho minus, or rather plus half of rho 1 over rho minus minus 1 over rho plus, okay, which is exactly this expression that tells you that your A must be pi by 2. Okay, so that's what you get. On the other hand, when rho is equal to rho plus, then you will get minus of half times 1 over rho plus minus 1 over rho, sorry, 1 over rho minus minus 1 over rho plus. Okay, so that means there's a minus sign, and that would tell you that A must be minus pi by 2. Okay, so that's how you get it this way. Just straightforward substitutions will tell you what are the angles. Okay, so the integral that we were supposed to do, which was not written anywhere actually, but when you kind of find out the 5 values, you will have to do this integral. That integral written in terms of a variable is from minus pi by 2 to pi by 2. Okay, so if you kind of write down a sign correctly, then it gets pi by 2 to minus pi by 2, it doesn't matter. Okay. Okay, but the integral is quite easy because a lot of quantities are just constants. There exists only one term which is sign dependent. Other terms are going to give you factors of minus pi at various places. Okay, there's a sign sitting outside, so it's actually really plus pi. Okay, so you have factors like that. There's only one place where this function multiplies gm into 1 over thing. Sine integrates to minus cos, so there you have to just keep track of that sign which is sitting around here. Okay, fine. So that is it. So what you need to do is to just collect the pieces and kind of simplify the expression a bit. You get a term which is where you can pull a factor of pi outside, and you have one term which is just 1 times pi factor. Then there are gm multiplied by 1 over rho plus 1 over rho minus pieces. You can see that they add up to 3 by 2 factor. And then there are terms which are proportional to gm squared with this, with that, and so on. Okay, good. Okay, so so of course, exactly the way we did this computation for the scattering problem, here also we will have to worry about doubling the angle, because what we are doing is going from rho minus to rho plus in this particular case, but the bound orbit would take you from rho minus to rho plus and back to rho minus, or the other way around. Okay, it doesn't matter. So so the difference of phi that we get here has to be doubled. Okay, so that is the one which, so that would give you a factor of 2 pi from the first term, and then the next term will give you pi times, oh, I forgot to write pi here. Okay, times 3 gm into 1 over rho plus 1 over rho minus. Okay, so that is the factor. Okay, now of course, if it was a simple elliptic orbit, it should have given you just 2 pi. Okay, but the fact that it is not 2 pi, that means it is not the same orbit all the time. Every time the orbit is kind of moving a bit. Okay, is kind of summarized in this additional term, and it tells you that the orbit is actually precessing about its center, or rather about its focus, and this is the additional angle. And of course, this quantity is still very tiny because compared to say 2 gm, in this particular case 3 gm, it doesn't really matter 2 versus 3. Compared to 3 gm, both rho plus and rho minus are pretty large. Forget about the orbit of say Earth. Even for the orbit of Mercury, rho plus rho minus are pretty large, and for this precession is a very tiny effect. but it's still measurable, and of course has been measured. So, what one finds is that after completing one revolution, the planet actually doesn't come back to its own position, but it is actually a bit shifted, and the orbit keeps kind of shifting around, and of course making several number of revolutions, that the orbit actually comes back to original one. Okay, so here's some estimate of this thing. That if we use m to be the mass of the sun, then this formula would correctly reproduce the well, there's no real estimate really. I haven't done this calculation. Okay, would reproduce the observed precession of the perihelion of the Mercury. Okay. Now, as I said, that the orbit will of course come back to its original orbit only after it has done certain number of revolutions, and the number of revolutions is basically given by 2 by 3 times rho plus rho minus upon gm times rho plus rho minus. Okay. Now, it may give you an impression that like this calculation is coordinate dependent, but in fact it is not. One can choose any other coordinate system and you will find that the precision of the perihelion is still given by the same factor. Of course, the variables would be different simply because you are choosing different coordinate system, but it's a physically observable effect and it's independent of choice of what coordinate system you have. Okay, so I think what I'll do is I'll stop here. We'll continue next time.